working principle. And these inductive transducer works based on varying the inductance. And what are the different ways of varying the inductance? By variation of self-inductance, mutual inductance, eddy current. Let's first see the derivations and physical interpretations of variation in the self-inductance. So I told you that when there is a current in the coil changes, the magnetic flux, flux lines linked with the coil changes, and because of the flux lines linked with the coil changes, there is an EMF induced in the coil. That EMF will oppose the cause producing it. Okay, so if that EMF is induced in the same coil, and then the inductance is called what? Self-inductance. So self-inductance of the coil can be defined as N squared by R, where N is the number of turns, R is the reluctance of the magnetic circuit. So what is that reluctance? When there is an EMF induced in the same coil, there is an opposition. So the magnetomotive force that opposes the magnetic flux that it produces is called R. So this is a resistance to the magnetic flux lines. This is just like in the electrical theory. In the magnetic theory, R is called reluctance, while in the electrical theory, R is called resistance. So reluctance of the magnetic circuit is given by L by mu A. And okay, L is what? L is the length of the magnetic path or length of the conductor, and area is the area of the magnetic path or area of the conductor. Okay, so the magnetic path is proportional, magnetic path length is proportional to the length of the conductor that produces it. Okay, so basically there is a length of 2 centimeter of a power magnet. The magnetic flux lines is basically going to run from north to south pole. The length of the magnetic flux lines is approximately 2 meters. Okay, so that's what L and A represents in the formulation of R. But what is mu? Mu is a permeability. So if I say it, and it's a permeability of a material, it's a property of a material. So if the mu is greater for for a given material, you can say that it is in a given magnetic field that the greater permeable material have a greater attraction force towards it. That means mu is defined as B by A, that is mu is B by H, that is the magnetic field strength divided by the magnetic field intensity on which it lies. Okay, and B is the magnetic field that produces the magnetic flux. Okay, so that is permeability, and based on this formulation you substitute in the L, and you will arrive at N square mu by G, where G is geometric factor, which is A by L, area divided by length of the magnetic path, is given as geometric factor. So now if you see this equation, L can be changed, self-inductance of a coil can be changed by 3 ways. One is change in the number of turns, permeability of the medium, and G is the geometric factor. Okay, then we know that when current is passed through one conductor, flux is induced to it. So that is N d the flux is equal to Ni by R. And when you differentiate this, what you will be getting is by UV method, U by V squared method, you will arrive an equation something like this. And if this equation, if this terminology is very large, you can remove it, and then what you will be getting is N by R di by dt, and EMF induced in the coil is given by E equal to Ni di by dt. So then you substitute this value in the previous equation. What you will, so you substitute this value here, so what you will be getting is N squared by R di by dt, and E by di by dt that we saw in the previous video is basically the inductor, that is N squared by which in turn is, can be written as N squared by magnetic reluctance R. Okay, so this is some quick formulations that you need to be clear with. Okay, so this is so now you could have understood that self-inductance of a coil can be changed by 3 ways. One is number of turns, second one is permeability, and third one is what? Geometric factor, that is A or L of the magnetic path length. Okay, we will see then what are the remaining stuff in the preceding videos.